Let's take a look at this concept question to start off the homework video guide. And for this first problem, we have a physics exam booklet, and it's lying on a table in front of you, and it is in translational equilibrium because. Okay, so when you're in translational equilibrium, that literally means the object it's at rest or it's not moving. And if you're not moving, that literally means the sum of the forces acting on that object is equal to 0. And that literally means that all the forces acting in the horizontal direction, denoted by the x variable, that's going to be equal to 0. And all the sum of the forces acting in the vertical direction, that's also equal to 0. Now, since force is a vector, sometimes you might see the hat here. Okay, and if I go back to this question, the best answer here would be option B. The forces acting on it are balanced, and if the forces acting on the object are balanced, it means that it's not moving, it's at rest, and that literally means that all the forces acting on that object are equal to 0. Okay, so that is the definition of translational equilibrium. All right, let's move on to the next question. So this next question, we have a definition question here, and we need to state the condition for translational equilibrium. And we just talked about this in the previous question. So this literally means that you're not moving, or you're at rest, and that means that all the sum of the forces acting on that object is equal to 0. So option A is your best bet there. So once again, if the sum of the forces is equal to 0, that literally means that the sum in the horizontal direction, all the forces in the horizontal direction are equal to 0, and the sum of the forces in the vertical direction are also equal to 0. And because force is a vector, we can also just kind of put the vector notation right there to finish that off. But there you go. There's the definition for translational equilibrium. Let's take a look at a calculation problem now. And for this next problem, we have two forces that are acting on the object as shown. So my two forces are F1, which is 25 newtons, and F2, which is 40 newtons. And my object is this thing right there. And we want to find just the magnitude of the third force required to achieve translational equilibrium. Okay, so just remember, when we're dealing with translational equilibrium, that means the object is not moving, and the sum of the forces acting on the object is always equal to 0, and we can also put this hat in there because a force is a vector. Now, if I go back to my picture here, what we want to do is we want to construct a triangle and show that the sum of the forces acting on that object is equal to 0. Okay, so we're going to add the vectors head to tail. So my first vector is in the north direction right there. So if I go ahead and just redraw that over here on the side here, here's my north vector. That's F1, right? And then I have my second force, which is going in the it's going in that direction right there. So this is going to be F1, the first vector, the first F1, which is the first force, and I also have F2, which is the second force. Okay, and what I need to do now here is, since I started over here, I want to construct a vector diagram where the sum of the forces is equal to 0. So what I do now is I draw my third vector starting over here, and I go back to my starting position, and this is my third vector right there. So in this vector diagram, what we're doing is we're adding the forces. And since we end up in the starting position again, we just add the third force there. And this is what we mean by the vector diagram being equal to 0. We add up all the forces, and since we start and end at the same position, our vector diagram is going to be equal to 0. And this is what we mean by the sum of the forces is equal to 0. Okay, so there's the concept there for translational equilibrium. And what we want to do now is we want to find the magnitude of the third force. Okay, so I go back to my triangle here. Let's go ahead and start plugging in some numbers here. So in the north direction, which is the first force, I have 25 newtons in magnitude. And in the east direction, I have 40 newtons. And for my third vector, let's just kind of label this as F3. Third force. All right, so we want to find the magnitude of this third force to achieve translational equilibrium, and in order to do that, we need to use the Pythagorean theorem because we have a 90-degree box right there. Okay, so if I go ahead and use the Pythagorean theorem here, we have our third force, and I'm going to square that because that is the hypotenuse, and then we just add the legs here, so 25 squared plus 40 squared. And if I just go to a calculator here on the right hand side, 25 squared plus 40 squared, that gives me 2,225. And then finally we just take the square root of both sides, and the magnitude here of the third force is going to be equal to 47.169 newtons. Right? So that's the magnitude that we need in order to achieve translational equilibrium. Let's take a look at the next problem here, and for this next problem we have a 220 Newton bag of potatoes, and it is suspended from a rope as shown in the diagram below. Alright, so here are your potatoes, and since the potatoes are suspended, that generally means that the sum of the forces acting on that object is equal to 0, meaning it's not moving and it's in translational equilibrium. Then the question states that a person pulls horizontally on the bag with a force of 80 newtons, and we want to find the tension in the rope. Okay, so our first option here is we should draw a free body diagram. All right, so let's find all the forces acting on the object. So this vector right here, that's kind of your force tension. And the bag of potatoes here, it has a force of gravity acting in the downwards direction. And we also have a horizontal force in the left direction, so I'll label that as F with a subscript of X. All right, so there's my free body diagram right there. And then the second thing that we want to establish is that we want to say that the sum of the forces is equal to 0 on that object. All right, so this is another translational equilibrium problem. Okay, so what we're going to do is, if I look at my vector diagram here, from my free body diagram, we need to construct a triangle out of this, and hopefully we'll get a right angle triangle here. So here is my force tension acting in that direction there. So I'll just kind of label this as my force tension, and I'll put a vector sign there, and then I'm going in the downwards direction for the force of gravity. Call this Fg. The vector sign there, and then my last vector here, in order to create translational equilibrium, I'm going to draw in the horizontal direction going to the left. So here's a rough sketch of my vector diagram here. I'll call this Fx with the hat there, and there is my vector diagram. And since I started here and I end there, we have established that the sum of the forces on this object is equal to 0. Okay, so what that really means is, from the vector diagram, that the force tension, and we're adding that to the force of gravity, and then we're adding that to the horizontal force in the left direction there, and that all equals to 0 right there. So based on this vector diagram, we have established that all the sum of the forces acting on the object equals to 0, and thus we have translational equilibrium. Okay, now what we need to do is we need to find the tension in the rope here, so we want to find the magnitude of our hypotenuse here. Okay, so if I just erase all this, and let me just kind of draw another diagram here so that's all connected now. So we had our force tension like that, we had our force of gravity like that, and then we had a force in the horizontal direction like that. And from our triangle, we have a 90-degree box right there, and we'll call this our force tension, which is what we need to find. The force of gravity had a magnitude of 220 newtons. The force in the horizontal direction had a force of 80 newtons. And now we have enough information now to find the magnitude of the tension in the rope there. And once again, we're going to use the Pythagorean theorem. So we're going to square the hypotenuse, and then we're going to square the legs of the triangle. So 220 squared plus 80 squared. All right, so if I add this all together here, on the right hand side I get 54,800 newtons, and then we have to take the square root of both sides, and our force tension here for this particular problem is going to be 234.094 newtons. Now if you want to round this down to two sig figs, you can just write 230 newtons as well. So both answers here are acceptable for this particular question. All right, in this next question, we now have a 25 kilogram block and it's being pulled by a horizontal force, and the supporting rope can withstand a maximum tension force of 620 newtons, and we want to find the maximum angle that the block can be pulled without the rope breaking. All right, so if we're trying to pull this block backwards without the rope breaking, then we're basically in translational equilibrium, and basically that means all the forces acting on that block are equal to 0. Okay, so the very first thing we want to do for this particular problem is we want to draw a free body diagram, and then the second thing is that we want to set up the translational equilibrium definition where the sum of the forces acting on that object is equal to 0. Okay, so let's go ahead and draw a free body diagram here. So we have a force acting in the horizontal direction here, so we'll label that F of x. And then we have a force that's acting in the downwards direction, which is the force of gravity. And we also have a force tension acting in that direction, so we'll call that Ft. Okay. One thing that you might want to do is you might want to calculate the force of gravity, which is really the mass times the acceleration due to gravity. And the mass of the block is 25 kilograms. The acceleration due to gravity is 9.80. And if I multiply those two numbers together, I get 245 newtons. Okay, so basically there's 245 newtons of weight acting in the downwards direction. Okay, so that right there is my free body diagram in the red font. And then from the free body diagram, let's go ahead and go into the translational equilibrium definition here, which means the sum of the forces is equal to 0. All right, so if I add the vectors from head to tail, here is my force tension acting in that direction. Here's my force of gravity acting in the downwards direction. And finally, if I want to achieve translational equilibrium, I need to go back to the beginning here, and I'll label that Fx with the hat there because it's a vector diagram. And this right there, we have now shown that if I add the vectors head to tail here, and since my third force here gets me back to the beginning position, this literally means all the vectors equal to 0, and we have established that the sum of all the forces acting on that object is equal to 0 there. Okay, so now that we've done that, let's go ahead and now let's label the triangle, and let's go ahead and find the angle that we are looking for, right? So let's go ahead and label this. So we did establish that this was 245 newtons acting in the downwards direction. The tension in the rope is 620 newtons, and our objective here was to find this particular angle there, and this angle right here is really this angle right there. Okay, so let's go ahead and put a theta there because that's the missing angle that we're looking for, and here's a 90-degree box there, so now we have a right angle triangle. Now in order to find the angle there, let's go ahead and analyze our right angle triangle here. So the 245, this is your adjacent, and the 620, that's going to be your hypotenuse. So using trig ratios here, you have your adjacent, your hypotenuse. So the acronym you can use is cos. So therefore we're using the cos of the angle. So cos of the angle is equal to your adjacent, which is 245, and then we divide that by the hypotenuse, which is 620. And in order to solve this particular equation where we want to isolate for the variable here, the angle there, so in order to do that, theta is going to equal to the inverse of cos, and then we go 245 divided by 620, and then we just go to our calculator there, and we just round the two decimal places, and we should get 66.72 degrees right there. So that is the maximum angle that the block can be pulled without the rope breaking. Here is the last question for this video guide here. So in this problem, we have a 45 Newton block that's suspended. And if the block is suspended, it literally means the block is not moving. So this is a nice little indicator that we're dealing with another translational equilibrium problem. And let's take a look at the rest of the diagram now here. And what we need to do is we need to find the tension in the horizontal cable. Okay, so let's go ahead and draw a free body diagram. So there's force in the, there's tension in this cable over here. So I'll label that as force tension. I'll call that force tension 1, and we also have another tension in the rope there, which is force tension 2, and we also have a force acting on the block here, and there's a force of gravity acting in the downwards direction. So there you go, there is our free body diagram. And then from our free body diagram, we want to go into the concept of translational equilibrium. And that means the sum of the forces acting on that object is equal to 0. So let's go ahead and draw another right angle triangle here. So here is the force, the first tension in the rope. Okay, and then we have the force of gravity acting in the downwards direction, which is Fg, vector notation. And then we have a force in the rope, force tension acting in the horizontal direction, which is force tension 2 with the hat there. And there you go. There is our vector diagram, and we just established that the sum of the vectors here, and since we start and end at the same position here, the sum of the vectors equals to 0, and once again, this is really the sum of the forces all adding to 0 on the object there. Okay, so that right there is the concept of translational equilibrium. Here's the vector notation there. Now, in order to find the tension, we now need to kind of plug in the numbers here, and what we want to do is we want to find the magnitude of the force and the tension there. Okay, let's go back to our diagram here, and let me kind of erase some of the colors here. Let me kind of blow this up here. So we have a 65 degrees right there. So if I kind of look at my triangle very carefully here, that 65 degrees really translates to this angle over here. So this angle right here is 65 degrees. All right, so if that's 65 degrees, then this angle here is also 65 degrees. And that's just the alternate interior angles concept. And we also know that this is a right angle triangle there. And if you want, you can go ahead and find that other angle there in the corner there. So this would be 25 degrees right there. Okay, so we kind of find all the missing angles there. And we also are given that the weight of the block is 45 newtons. And that translates to the magnitude over here being 45. And basically, we want to find the tension over here, right? This tension is really that side of the triangle right there. Okay, so we have more than enough information now to solve this particular triangle here. We have angles, and we also have a side there, right? So let's go ahead and use, it doesn't really matter what angle we use here, but let's just use 65 here. So this right here, the 45 is going to be the opposite, and this side is going to be the adjacent. All right, so if I have my opposite and my adjacent, I'm going to be using tan of the angle. So tan of the angle is going to equal to your opposite over your adjacent. All right, and the angle that I'm using is 65 degrees, so tan 65 degrees, and that's going to equal to my opposite side, which is 45, and my adjacent is just the tension in the rope there. Okay, and now our goal now is to solve for this variable there, the tension there in the rope, so I can just isolate that by moving that to the left-hand side. 45 remains on the numerator. The denominator will be tan of 65 degrees. And then from here, you're just off to the calculator here, 45. Sorry, this 5 isn't that great. So 45 divided by tan of 65 degrees, and that should give you 20.983 newtons. And if you want to round this to 2 sig figs, 21 newtons is also acceptable there. So either answer here is good enough there. All right, so that concludes this first homework video guide on translational equilibrium.